Well, so this is part 2 of the class, and we talked about the concept of trying to deduct percentage. And the purpose is just to know, people will be more interested in knowing what is the percentage of heat loss. When you say I'm going to reduce the heat loss by 50%, 20%, 30%, that will make more impact when you communicate with the client. So we say there are many ways to do it. You can do it in a calculator if you have a function, but everybody does it differently in their head. So 3,000 minus 30%, you can say 30% is what's going to be taken away. So I'm left with 70%, so I can multiply my number by 0.7. And if you put 70%, what is 70%? It's 0.7. But if you put in the calculator 70%, it will think it's 0.007. Calculator can understand it differently. So I don't know, John just did his calculator and it was kind of confusing. But for me, 70% is 0.7 because it's part of 400. So 1% is 0.01, right? It's 1% because after the decimal, every 0 is part of a 10. So there's two ways to do it. Either you multiply by 0.7 and get on with your life, or you can find out what is the 30%, which is 900, then subtract that from the original price. Lengthy way to do it. We give the example of paying your bill and trying to calculate the tip. It's 20. If you want to do 20%, for each 10 it's going to be $2. So whatever way that's easier for you to do it, go with it. So let's do another example here. Calculate the heat loss for per hour for a room that has only one wall facing the outside, with an area of 8 by 12. Wall U factor is 135. The inside is at 85, and the coldest outside temperature is 10. So let's do the first part, which is finding the heat loss. Q equals area times U times delta T. I'll go with area. Area is 8 by 12 times the U factor is 0.35 times 85 minus 10. What is 8 times 12?
96.
Huh?
96.
96. Thank you. 0.35 times 75. That will give me 2,520 BTU per hour. Okay. Now, to make things a little interesting, let's see. We want to reduce the heat loss by 38%. Why 38? I have no idea. Just an abrupt number, so you can't do it in your head. So
0.3.
either I will multiply. So heat loss nu will equal 2,520 times 0.68.
0.68.
That's the remaining of 38%.
62.
62? Oh, sorry. Oops. So, if I do it this way, 2,520 times 1 minus
your answer is
0.38. Same thing. Or you can do, let's do it. So 2,520 times 0.62, 1,562.4.
Oh, okay, I got that. I did something different, but yeah.
Okay. It's the same thing.
Yeah.
Or you can do it the other way.
What's that
Say,
now? Oh, sorry.
you can do it the other way. 2520 times 0.38, that's equal 2520 times 0.38. That will give you 957.6. That's what you going to take out. So you go back and do 2520 minus 957.6. That should be 52.4 BTU per hour. It should be the same number. Whatever way you find it easier, go with it.
So now we use that R insulation, the area times delta T divided by Q. We use that equation, correct? No?
Yeah.
Alright.
So now we're trying to see what is the R insulation that I'm required to put in. So first, I need to do the R insulation equation. Area times delta T times Q, and with the new one, minus R wall. And I'll do the R wall here. Equal 1 over U, equal 1 over 3.35, equals what? 2 point something?
2.857 or something like that, but round up to 2.86.
2.85, that's enough. Okay, now I just fill in the blanks. Area, we said the area was 96. Minus 75. To 1562. 4 minus 2.85. What do you got?
1.75.
Oh yeah. 6 times 75 over 1562.4 minus
So we're at the third, wait,
1.75.
the 30, we're the,
We're looking for.
how do we wait,
You take the new number, what you're trying to figure out how much it is by. Is the 1562, that was the 38%.
oh, right, yeah.
So that's the number you use instead of the 2520.
Oh, okay.
When you do the division, and then you minus the R value of the 1.35, or the 3.35, which equals to 285.
Okay, so you do the percentage at the beginning, essentially,
Yeah.
okay.
Because you want to put the Q new here.
Oh, so that's the new Q,
Yeah.
oh, okay,
Because we're trying to find the R insulation.
okay.
So we want to reduce it by 38%. Okay, this is my original heat loss. I want to reduce that by 30%, by 38%. This is what I'm aiming for now. I'm shooting to have 1562.4. Okay, this is my goal. I'm gonna put it over here with the same parameters. Nothing changed here. Are all the
Yeah.
same. Everything is the same. We just have different Q. Based on that, we can find the new insulation. So probably I'm gonna go with 2. We're not gonna find 0.7, so we're gonna go to approximately R2 insulation. And R2 is not difficult to achieve. There are sheets, or half an inch. That's R2. And also you can change the gypsum board. Some gypsum board are insulated. So you can change the drywall, probably that will do it. And again, please, if you are going to renovate a house, or buy a house, or build a house, do not skimp on the drywall. Skimping the drywall is the worst thing ever. There is drywall for like $5 and there's one for $40. I've seen houses so is so upsetting because the cheap drywall will start flaking after a while. It has no insulation. You cannot put a nail to it. It just, I don't know. It's very thin. Does not do a good job.
So you want to lean on the wall and punch a hole through it.
Yeah, and it gets crispy after a while. It dries after a while, and the adhesive in it goes away, and it's very expensive to change drywall. So taking it out, it's a lot of nails. The labor that involved to change drywall is so tremendous that it's completely not worth it. So it's better to start with good material. People will say, I'll put it in, then I will change it in 2 years. You will have furniture there. You have people living there. You're gonna move everything out, change everything, clean it out. Then put why don't you start with like really good stuff from the beginning? I'm always against using cheap material, no matter what. You know, I mean, because you're gonna pay for it later on. So drywall is important, and now they have drywall with really good insulation in it. You'll pay like maybe $40 a board, maybe $80, but it's completely worth it. And you'll know the worth when you see that, the R value. Come with the R value. And some of them are actually, they look the same, they have the same thickness, but they are different density. One of them you can put a push pin through it. And some of them you can't. It's so dense, it's so well made, it's so strong you cannot push any nail through it. And I found that the houses built in the 20s and 30s, they had better drywalls than the new ones. Like the new ones actually with your nail you can scratch over the gypsum. The old ones are so solid you can't even drive the nail through it. So it will last longer, it will hold shape, and also it will not react with moisture the same way. Some drywall, if it gets moist, it starts like sagging and flaking and pulling apart. So again, this tells you the difference in insulation and how the R2 value is going to give you a reduction by at least 40%. That's significant. That is significant in a wall facing the outside.
So when me and my dad are trying to do in our basement is, so about a year and a half ago, my mom had me buy those like 4x8 sheets of the insulation.
Yeah.
I still have to do finish it, but she had me cut and put it in between the floorboards.
Yeah.
Then my dad is gonna about some of the spray foam insulation, and there's a corner.
Yeah.
And everybody's where he said there's like a huge draft in.
Yeah.
So we're gonna like attack that.
Yeah, so there's another way, we talked about that, like in last semester, if you have a drywall that's really like not that good, you can actually cut a hole in the corner and pump some foam into it. It's not the best way to do it, but it's better than changing the drywall and starting all over again. And I asked somebody who do construction about changing drywall, because he was trying to scrape off the wallpaper.
Oh.
And I told him, why don't you just like change the drywall? It's really, really annoying. There's so many nails, and it's just a tough job to change the drywall. So he spent like 2 days just scraping off by hand wallpaper. Wallpaper went out of style.
Yeah.
Okay, so let's do this example. I want you to do it, and I'll see how you guys do. So heat loss of 12,000 BTU, wall 150 square feet, temperature difference 70. The wall use factor is unknown. What is the R value and what is the insulation that will reduce the heat loss by 40%? That's interesting example.
Oh, so we basically have to work backwards to find the use wall factor.
Yep. That's actually could be a live example. You go to a house, you don't know what the wall is made of. You can't cut through it to see what's going on, but you know there is a lot of heat loss from the wall. And how did we know it's 12,000 BTU? Probably this. You can know that by the size of the radiator in there. We'll talk about that later. But let's try to work backwards and see if this will happen. We'll go up some more.
So what would be the area?
The area is 150.
Oh.
Did you finish, Josh? What you good? That's what I thought.
Yeah.
Bill said he was gonna be out tomorrow too, or? Oh, okay.
We got 0.58.
Yeah.
Let's look at it now. This is the problem, and I'll go through the steps. Okay, so we start with 1200 BTU hour. Delta T is given, area is given. So I had to work my way backward to get the U factor, which could be a real case sometimes because you don't know what is the U factor for the wall. And I started with Q equal area times U times delta T, and I divided by area, then divided by delta T to get the U, which So the U will equal Q over area times delta T. This pen is bad. And I hope you have that in your cheat sheet. If not, you can put it in there. Let me see if it's there. No, it's not there. But you just have to work it back. Or you can fill in the blank here.
Yeah.
I'll put that. So we get the U factor, which is 1.14. I took it a step further, and I get the R value, which is 0.85. 1 over 0.875. So I use the other equation from here to get the R isolation. The new Q that I'm aiming for is minus 40%, so I multiply by 0.6. 60% is the value that I want out of the 120. I mean the R is 0.
Yeah.
12,000. Sorry, I got 7,200 BTU. This is what I'm targeting after I reduce the heat. I put those numbers in the equation, which is this one over here, and I get 0.58 as my R value. Any question about that? There.
If you flip your division, you don't have to find the R value. It gives you the R value.
So what was that 40%?
That's true. Yeah.
So,
Yeah.
So that
Well,
40.
depends how comfortable with math are you, you know? Yeah, if you're comfortable, do it. Go ahead.
No, that 40%. I was wondering at the beginning, what was that? That has.
What was the 40%?
Yeah. That was a
that's a-
factor. It's not a U factor.
No, the 4% is the reduction I want from the Q value. I want to reduce the heat loss by 40%.
Oh, by 40. So I was
Yeah.
minus. Okay.
You subtract the 40%. So this should be it. And let's go back. So those are like 3 examples so far, and it is worked out here in details in Blackboard. So if you get lost, you can find the steps in here. The effect of the wall, the R value, the new Q, the iron isolation turns out to be 0.58, so you just go up to R1, which is not a lot.
So in this case, with insulation, you would round up
Yeah.
instead of rounding down. You
No,
would
you round up.
Okay.
Yeah, because you're not gonna find one. If you can find 0.5, you're gonna off go with 1.
Well, if it was 0.51,
Yeah.
couldn't you go with a 0.5 R value?
Yeah. Yeah. You could if you find it.
Okay,
Yeah.
but it depends on how far you are from
Yeah.
the
Definitely.
lower number. Okay.
Makes sense.
So is that
Actually, yeah, go ahead.
that 40% is 0.877 minus?
Yeah. Say that again.
no, the 40%.
40%.
Is
Yeah.
the 7,200.
That's the 40%. So I want to take 40% out of 12,000.
Oh, okay, okay.
So I'll be having 60%, which is 0.6.
Right,
So
right.
you subtract 40% out of 12,000.
by multiplying it the 1,200 the 12,000 by the 6.6 by the
Because-
60%.
Yeah, 60%. You got it. Which 60% is 0.6.
6, right,
Yeah.
right.
Okay. So we get that. We'll do. I'm curious, what is the R value of wallpaper?
Probably not that much.
Yeah.
Probably.
Maybe they have new wallpaper that has really good insulation. That'll be interesting. Let me look it up.
I'll say, I mean, I want to say nothing.
The wallpaper I've seen, man.
I mean, the only thing I get to see it doing is just sealing a crack in the wall, but
Yeah, they do have thermal wallpaper.
well, it's the R value.
What is the R value? No. so far. The blaster board, which is the gypsum board, around like R3, which is not bad.
Really?
Yeah, from what I've seen so far. I will do some research on that because I've seen some wallpaper that has good insulation. It's very thick and made out of styrofoam material. So I think that has some decent insulation. Not the real small one.
Yeah.
It will do some insulation. Okay, so we'll do this. So we did this example. Okay, is more insulation better? This is also to give you an idea that adding more insulation is not always best. And let's look at this. This blog will explain the math. It's not working for some reason. So there's an article here. I put the link. It says the diminishing return of adding more insulation. You do not need always to add more and more. Like you can have, and they do the math for you to convince you that adding insulation is not always the solution for everything. And another YouTube for insulation and not having the proper insulation in the house. And just to convince you and do it from what we have been doing here in class, is it a good idea to add more insulation? So if we do the math, it's our equation, it's our R total, and I put the heat loss as variable with added insulation, and we come up with this equation here. So I will plot this equation with some constants. So if you look here, I fixed the DT at 65. I fixed the R wall because you cannot change the wall. I'm going to change the insulation. And the area of the wall is also fixed. And I just keep adding more insulation. So look, this is R1, all the way to 12. If you notice, at R1, the heat loss was almost 6,000. It dropped significantly, keep dropping. At 3, it dropped. Then we added 0.5, and not much. See how the change is not that significant? 300 BTU, and it keeps going and going until you get to a point where there is almost nothing, like 30 BTU. So you keep going and going. Between here and here, it's only 30 BTU per half an inch per R.5. Yeah.
So how much heat loss is the right amount that I'm willing to breathe?
Well, ultimately, you want no transmission heat loss.
Well,
Transmission, not infiltration.
Well, it's like, because if you get lower and lower, the insulation is preventing air from flowing.
No, but that's through the wall.
Oh,
We're
yeah.
not thinking about the infiltration. It's only transmission.
Oh, okay.
So look at this. I graphed the data. So you see in the beginning, you had huge drop, and then not that much until it becomes almost like nothing. So you keep adding insulation for no apparent reason.
Okay.
So this is your sweet spot where you know there's a big significant drop. Yes, that's completely valuable, and this is the insulation value here. Now since the BTU insulation, so the optimum insulation here is going to be around 2.5, 2.7. So I'll go up to 4, which is if I find that, and that'll be it. Any more than that, and I'm just wasting money. So that's something just to show you why adding more insulation is not always the best solution. And again, this is the calculation for it. Of course, you don't have to go with this extreme. You can just like spot that. You can go and see what is available. We have 2, 4, and 6. Do the math for those 3, and see which one give you the biggest change. And just keep it at that. It's impossible to have 0 heat transfer. Everything you will have heat transfer unless you have your house designed as a thermos. There's no way to have heat transfer. So it's gonna be there, but we want to be as small as possible. I mean, 6,000 and around 2,000 or 4. This is even better. That'll be enough to have significant reduction in heat transmission, which is not that bad. Okay, so this is what I have for this week, talking about insulation, capturing infiltration, and transmission. Thank you.